Hello, my name is Jason Bowen, and today we are going to be talking about two things, Lewis dot structures and formal charge. So let's begin by looking at Lewis dot structures. Lewis dot structures are a representation of the valence electrons of an atom, and they use dots around the symbol of the element to represent those valence electrons. So there are 5 simple steps to drawing a Lewis dot structure. Number 1, you're going to count all the valence electrons in the molecule. So for silicon tetrafluoride, which is our first example up here, look at your periodic table. We can see that silicon is in the 4th group, which means it's going to have 4 valence electrons. So 4. And then fluorine is in the 7th group, so it's going to have 7 valence electrons. And there are 4 of them, so we're going to do plus 7 times 4. So that would add up to 28. 28 plus 4 equals 32. So there are 32 valence electrons in the molecule, and you're going to determine the central atom, which is usually the least electronegative, and in this case that is going to be silicon, also because there's only one of it. So we'll draw silicon as our central atom, and then you're going to draw your single bonds, so, and connect those to the 4 fluorines. So each of these single bonds represents 2 atoms. We could also draw that like this, to represent that it's 2 atoms. So we can see that each of these will be 2, and that adds up to 8. So 32 minus 8 leaves us with 24. Going to the next step, put all the remaining electrons on the terminal atoms. So 24, and each of these can hold 6, so we'll do 1, 2, 3, 4, 5, 6 on each of them. And we see that that adds up to 32 total electrons. We have 6 in each of these, 24, and then 32. So we don't even need to go on to the next steps here. This would be the Lewis dot structure for silicon tetrafluoride. So let's look at another example that is not quite as simple. So then, again, let's follow these 5 steps here. We're going to count all the valence electrons. Back to our periodic table, C is in the 4th group, so it'll have 4. O is in the 6th group, so it'll have 6, and hydrogen's in the 1st, so it'll have 1. So we'll do 4 plus 2 times 1, since there are 2 hydrogens, plus 6. And we can see that that will add up to 12 valence electrons in the formaldehyde molecule. So let's come down here. We're going to determine which one of these will be the central atom. And because there are, because of electronegativity, we can see that carbon is the least electronegative, and that will be our central atom. So we'll draw C, and then draw your single bonds to the 2 H's and the 1 O. So we've got CH2O. We know that this adds up to 6 electrons, so 12 minus 6 leaves 6 left over for us to draw. We also know that hydrogen can only have up to 2 surrounding it, and there's already 2 here. So we're going to not draw it on those, and we're going to draw the 6 around the terminal atom here being the oxygen. So as we can see, we already have our 12, but let's go on to the next step. If necessary, turn lone pairs into double or triple bonds to achieve the octet or the duet rule. So as we can see, carbon only has 6 electrons around it, which means it's not achieving octet, versus oxygen, which here does have 8 around it, achieving octet, and hydrogen achieving 2. So how can we correct that? What we're going to do is take 2 of the valence electrons from oxygen and draw them as a double bond to this carbon here. So then we can see that carbon does in fact now have 2, 4, 6, 8 around it, achieving the octet rule, and oxygen here also has 2, 4, 6, 8 around it, meaning it has also achieved the octet rule. So this is going to be our Lewis dot structure for formaldehyde, or CH2O. Formal charge has 3 basic steps. You're going to calculate the formal charge. So formal charge equals the number of valence electrons in a free atom minus the number of valence electrons in the bonded atom. So let's look at an example here. We're going to be doing the resonance structure for sulfuric acid, or H2S, that's not a 2, H2SO4. So we're going to start by drawing the Lewis dot structure. We know here that, looking at the periodic table, S is going to be our least electronegative, so that'll be our central atom, and then we'll draw all of our single bonds. So there's our 4 O's, and then to our hydrogens. So if we add up the valence electrons here, we've got 2 plus 6 plus 6 times 4. So that's 24, 30, 32 equals 32. And we already have 2, 4, 6, 8, 10, 12. So we have 20 left to draw. So we're not going to draw it on the hydrogens. We're going to start with our terminal atoms. So there's 6 there, 6 there to give you 12. And then we see that there's room for 4 more on each of these. So that adds up to your total of 20. So there we go. That means we've drawn all of our valence electrons. And next we can start by trying to find the formal charge of each of these atoms. So looking, for example, at this oxygen, which is going to be the same as this one, we know that in the free atom of oxygen there should be 6 valence electrons. But here you're going to take half of what's in the bonded, so this would only be 1, plus the 6. So we have 7, which means the formal charge on both of these would be -1. So -1, -1. Let's look at the sulfur now. Sulfur here has 1, 2, 3, 4 around it. So that's in the bond atom, we've got 4. And in the free atom it should also have 6. 6 minus 4 equals 2. So this would have a formal charge of plus 2. And then this oxygen has 1, 2, 3, 4, 5, 6 in the bond atom, as well as 6. So that's in the free atom, so 0, 0. And hydrogen has 1 and 1, so that's also going to be 0. The next step of formal charge is we know that the sum of the formal charges must equal the overall charge of the molecule. So we have this overall molecule has a charge of 0. So we have -1, -1, which is -2 plus 2. That is correct. And we're trying to get the formal charges here as close to 0 as possible. What we're going to do here then is we're going to take 2 of the atoms from each of these oxygens and move them in to make a double bond with this sulfur. And what that's going to do is now we have 1, 2, 3, 4, 5, 6, so a formal charge of 0, 6 minus 6 being 0, again 6 minus 6 being 0, here again 1, 2, 3, 4, 5, 6, 0. So as you can see, we have minimized our formal charges here, so this would be our best Lewis dot structure, and it has formal charges of 0 on all of the molecules.